Hello again. Tonight we're going to talk about how you present waveforms, or what a waveform is and how you get the data to the point where you can see what's going on. So the goals of the presentation, this was a member suggested presentation. Thank you, Adam. It has non-trivial presentation goals because there's a lot of this, but not too much that kind of thing. So we're going to explain what a waveform is, various presentations of a waveform, kind of touch on the math to produce a waveform, but not get into the trigonometric sums and such. I do have a lot of links at the back of the presentation that you can get down into the minutia of the math of waveforms and Fourier transforms and such as much as you want. And I even have some that are mathematically oriented, graphically oriented, Python programming oriented, so all of that kinds of stuff. I'll explain what a Fourier series and what a fast Fourier transform is, without, again, getting into too much of the math. And there's links to YouTube videos at the end. And then how all that falls into creating a waterfall plot. Simple thing. What is a waveform? A waveform is nothing more complicated than a change in amplitude over time. You can have all sorts of shapes of waveforms, but it's essentially, if you have time moving along the horizontal axis, and then you have a varying voltage, and the voltage changes with time, this happens to be a sine wave. That's one form of a wave. This is called a sinusoidal wave or a sine wave. And I've scaled it to a fixed range of, it goes from -1 to 0 to +1. So it has a nice scale there. But this kind of wave exists in all kinds of things: acoustics and sound, various electromagnetic spectrum, infrared, visible, I should say ultraviolet or UV, X-ray and gamma, and then in radio from 0 hertz through terahertz. Contact pressure, pushing on things, air pressure, measuring the atmospheric and the altitude of things, springs. If you have a spring that you drop a weight from a spring and the spring bounces up and down, that's this sinusoidal waveform until friction and gravity and heat takes into account, and then it shrinks it. That's called dampening. All of the data that we're observing or capturing, we can display that data in multiple ways. We can display it as just numbers, just like raw data values that are ripe for algorithmic processing, but it starts out as just raw data values. Every so often you capture a sample, you record the sample, and then you record when it occurred, or you start a clock and the clock goes at a fixed rate and you just log the samples and know the rate. A spectrum, so you can actually see the waveform changing frequency, expanding and contracting in real time. Or you use math to flip things around and you display what is known as a waterfall plot, and we'll get into what that means. But you're changing the domain. You're switching from amplitude over time, and then you're rotating that around so time moves up. So here's a simple columnar presentation. I have an X and a Y coordinate from that sine wave that you saw, and then we have the value of the sine, and it goes over a specific range from 0 to 1 to 0. And you can take in values that are degrees or radians or the actual values of the sine curve. You're just plotting data. So you plot the data. Now, the data itself doesn't really care what the source of the data was. It could be audio, radio, light. It's just numbers. So until you start analyzing the data, you don't really know what you're looking at. So the first way of showing it besides just raw numbers is a spectral analysis. So the distance between peaks and valleys is a wavelength. And then the occurrence of those over a period of time is frequency. So if you were looking at something that was a fixed sinusoidal wave, the wavelength wouldn't be changing. But if you're looking at something like an FM radio signal, the distance between the peaks is changing because the signal is frequency modulated. So as voice gets modulated by frequency modulation, the frequency changes, so the distance between the curves changes. this is a static image, but this is a spectral image from a software-defined radio receiver. It's called SDR Sharp. The thing in the middle is just an indicator. There's nothing going on there. That's just how wide a signal I wanted to be able to zoom up on, or the bandwidth of it. And then you see over here on the left this spike. And that spike is actually a digital data signal. It comes and goes, changes from spike to, from not there to there. And then over on the right, this is actually a couple of channels of different kinds of modulated data. And it's not voice, it's actually data signals. There are two different kinds of pager signals, one-way pagers. They have different modulations on them. And then you can see a little digital data spike there. All this sort of hashy, zigzaggy stuff in the background, that is noise. When they talk about the cosmic microwave background noise, that's the universe. That's noise from the universe. And it's just there. That's back when they had analog TVs, and you would tune to a channel that didn't have a TV station on it, and you just see like white noise. That was the cosmic microwave background. Now, if you wanted to have a signal and then adjust it, you can do simple amplitude modulation. This is where you actually encode the data in your signal by increasing and decreasing the amplitude, the voltage of the waveform. Frequency modulation, you're compressing and expanding the waveform. And if you just want to see it bigger or smaller, you can just use the math and scale the numbers to make the wave taller or shorter or wider or narrower, and you're not actually affecting the signal, you're just affecting the presentation of it. So when I talk about software-defined radio and how the radio data is stored, the radio data is stored where every single sample actually has two values in it, the I signal and the Q signal. The I signal records the amplitude of the signal, so above 0 volts voltage. The Q signal records what is known as the signal quadrature. If you think of it as this corkscrew spring thing that you see here on the right, if you were to flatten that out, you would actually see, hey, that's my waveform. It's going up and down. But in 3 dimensions, you can stretch it out like a spring, and then instead of measuring the frequency of the wave, you just measure the position of the dots around 360 degrees. And once you have that, you can use sine and cosine functions to reproduce the wave and actually analyze the frequency of it. So all you need is an I for the amplitude and a Q for the signal quadrature, or trigonometric angle of that point on the curve. And now you can do all sorts of math with it. But once you have the data in this trigonometric form, then you can start doing that Fourier transform stuff. So here's that signal in flat 2D, and you can see there's my sine wave, and you can see the little crosses on there, the points. But if I were to take that and rotate it and stretch it out in 3D, you can now see my 0 to 1 becomes a +1 to 0 to -1 across it sideways, and my normal 0 to 1 is over here. And now I can measure my data points by at what angle around the coil my sample is. And then time is measured here across the bottom. I'm sampling my data as if it were a dial being rotated around. And when I turn it to 2 dimensions, I get my curve. I get my sinusoidal wave curve. But once I have the data in this format, I can do all sorts of interesting math on it. So without doing it as an animated waveform, or without showing you all the trigonometric factored sum series, this top one, that is a square wave. You see it goes up, squares, come down, square. But the little ripple that you see there, the pink one, that's a sine curve. So if I start with just a sine curve, I get my sine curve. But if I throw in additional waveforms that are factored to be smaller or narrowed amplitude, I can actually synthesize my square wave using a long series of sine waves that are different factors. It starts out very much not like a square wave. And then as you add more to it, it gets squarer and squarer. Now, the graphic that I picked up for this, I deliberately didn't get a perfect square wave out of it, so you can see something called ripple. This is where the signal that you're getting actually overshoots or undershoots the real signal you're trying to achieve. This is a sawtooth wave. This is a triangle wave, and this is let's see, we've got a square wave, a sawtooth wave, and a triangle wave. There we go. So different kinds of waveforms, but they can all be synthetically reproduced with a long enough series of math formulas. And I'm not going to get into the math formulas because that gets a bit heavy, but if you want them and you want to see the animated graphics, there's links at the end that you can go do your post-presentation session homework. Adam did some of this before the presentation. I wasn't soliciting people to go do homework. It's more a matter of, if you're interested, there's links that provide videos. If every time I wanted to reproduce a waveform, I had to have this near infinite sum in order to get my waveform exactly the shape that I wanted it, that would consume a lot of the horsepower of my computer. And remember, I'm now doing this, but under $20 computers, so I don't have a lot of horsepower to waste. How do I get my waveforms to be more exacting to what I want without having to run these series out to infinity, or you have several hundred terms to get it approximated to just what I want? And that's where the fast Fourier transform comes in. So if I know my sensor that's collecting the data is, let's say, 8 bits wide, I know that the maximum value is 255 and the minimum value is 0. So I know in advance all the possible input values. If I know all the possible input values, before I ever start analyzing the data, I can create myself a matrix table of, if this is the input, and then I'll run out a really long, fast Fourier transform and come up with the result number. And then I'll do that for the entire set of values. So now I have a way of just going, if the number is this, the output is that. If the number is this, the output is that. So when I'm plotting or displaying the data, it's just a set of discrete values. Here's the input, there's the output. There's very little math actually being done to do the live transform. So this is why it's called a fast Fourier transform. When I first started researching this, I went, why do they call it fast? Is it because, well, you start out with this presumption you're going to do an infinite series of summations, and then, well, once I get more than 20 sums, the difference between the signals is not worth worrying about. So I'll just clip it at 20, and that's still not slow enough, because if you're doing that for every data point as it comes in, doing all of these trigonometric and squaring values and then summing all of that up, that could be milliseconds of small computer time per data point. Don't have any time to do that. But if I know the maximum range of my data values, I can pre-calculate within a matter of a few seconds all the possible values, all the way out to 16-bit values. Having a computer have a table that has 65,000 entries in it, that's pretty easy these days because you've got gigabytes of RAM. So if I know my width of my values, and I know my quadrature signal, which started out as a cosine, now I can do all sorts of mapping very fast. So if I want to increase or decrease the amplitude of my waveform, it's just adding the value. So if I have a value and I want to take my discrete set of values in the table and amplify it, it's pretty easy to just add some value to all the possible numbers, and now my waveform gets taller. So when you think about, hey, the audio wasn't good enough in my video, I'm going to select this section of the video and I'm going to amplify via the computer the audio signal. Well, all it does is it creates a fast Fourier transform of the waveform, and then it adds a value to it, which boosts the waveform and amplified signal. And it's done like that. So if we want to reduce the amplitude, we can subtract. If we want to amplify it, we can add. If we want to modulate data, instead of adding a fixed value to my signal, I can take my tone, my carrier, and then I can add in the amplitude of my microphone samples, and now I've amplitude modulated my waveform. So it's pretty easy to do amplitude modulation, but AM is not that resilient against all kinds of noise. So you want to maybe do it in frequency modulation instead of amplitude. But as you can see, once I have my Fourier series and I've done my fast transform and I have my table of my discrete values, doing basic math on the waveform signal is not magical. It's pretty straightforward. But they make it even better if they dedicate a little tiny computer that is specifically designed in its instruction set to do these kind of things, like do the Fourier transform, do the amplitude increase, do the amplitude decrease, do the amplitude modulation or demodulation. You can subtract, if you know what the carrier is, you can subtract the carrier out and get your original audio. All of these little things you can do with the signal, because now you've got it as math, not just analog. They have dedicated processors for doing this stuff called digital signal processors. And where are those that everybody would be unaware of, but they're there? In your mobile phone. Every mobile phone has a digital signal processor in it. And it's just, they make them so small now, it's just thrown into the central processor like a little add-on. You know, they'll sample stuff millions of times per second and then do the waveform analysis, and it makes your voice sound clearer. You know, it allows you to receive and demodulate things like GPS signals and know where you're at and be able to take that data and put it on a map. So your phone is doing all of this magical digital signal processing stuff, and it's doing math, but it's doing math using tables, not using hardware instructions.
Monroe, I have a question.
Sure.
This is hardware or it's not hardware?
The digital signal processor is hardware, but it runs very simplistic software programs that have very few instructions, so it can do them very, very fast, but it doesn't get, you know, if they need to do an algorithm like a fast Fourier transform, and it's mostly sine waves, they may actually have an instruction that is a successive approximation instruction that it does like the entire cycle for the waveform in one instruction step. So it does it very fast. So the digital signal processor is not a general purpose computer. It's dedicated.
So if you drop your phone,
yeah,
is this something that's sensitive, and then that's why you have like sometimes a problem hearing things that are going on when you use the phone again?
No.
Okay.
I don't know what that. I don't know what that is, but there are other chips in your phone called micro electromechanical systems, or MEMS chips, and they will measure things like atmospheric pressure, magnetic fields, like what's true north versus compass north. If you drop your phone, the accelerometer will pick up the fact that the phone is falling. So there's all kinds of very small scale, very high capability electronics inside just a cheapy mobile phone these days. And you don't know it's there. It's like a car. Cars have all kinds of electronics in them. But do you need to know how all that stuff works from a design and architecture spec in order to drive your car? No, they simplify all that stuff. Same thing on your mobile phone.
Yeah, but when you get the mobile phone back from them and they said, we've repaired such and such and such, you'd like to think you knew what you were talking about sometimes.
Well, since everything is embedded electronics and it's all surface mounted chips, they'll say things like, we replaced your display. Okay. Or we replaced the main board. Okay. They're not going to get down into the detail and say, we replaced the MEMS chip that was responsible for your XYZ accelerometers.
I guess the guy didn't know not to talk to me about MEMS chips last night, because that's what he was talking about with MEMS chips.
Yeah. Well, the MEMS chips these days are so small, they're actually embedded in what is known, because it's not just the central processor, they actually have what is known as an SoC, a system on a chip. So they take the central processor, RAM, ROM, all kinds of sensor stuff, and they throw it all into one chip, that is smaller than a postage stamp and probably the thickness of a playing card, and that's the central brain of your mobile phone.
Yeah, but I got the sense that there was something with frequencies. What he was telling me was a problem when I dropped the phone that caused it. And this was a long time ago. This was on an old phone, so I don't even know if this would be true for a phone today.
Yeah, up until they have MEMS-based microphones in phones, you would have an acoustic receiver that would be your microphone. And if you got that exposed to water or you dropped it on it with too fast an acceleration, it could affect the little tiny mylar cone microphone that would be in there or the speaker. And so, yeah, it would make sound funny when you were speaking, or it would make, when you're hearing somebody on the phone, it'd make them sound very tinny.
But that's not a waveform, though, or is that a waveform?
Well, anything that's acoustic is a waveform.
Okay, then I was okay. Then this wasn't totally off the beaten track. Yeah, they are waveforms that it's affecting. Yes. Okay, yes. Thank you.
But as you get into things like deep space communication with Voyager 1 and such, you start getting into multiple layer, very exotic modulations like BQSP. And the reason for that is it has some redundancy for all the static that it's going to encounter in the billions of miles it takes to get to and from the deep space probe. And yeah, it takes a little longer to decode those signals. But since the signal's been traveling for 2.5 days, it's okay if you take a half a second to process the signal. So once you have your waveform into an I and Q format, and then you run it through a fast Fourier transform, you can now take the data and literally rotate it. It's kind of like in an Excel spreadsheet when you rotate the horizontal and vertical axis. Well, in this particular case, what we're doing is, instead of frequency doing this and amplitude doing this, we now have data points scrolling on the screen. They can scroll up or scroll down depending upon the software. But as they scroll, each line is a sample in time. And the width of it is your band spread. It's the actual frequencies of the signals. And then the brightness of it is the amplitude. So if a signal quickly changes frequency, it'll be colored to be like something that stands out more. If your frequency is very narrowly changed and not very high in amplitude, it'll be like on the left here, this little reddish dotted vertical line. But if it happens to be a very broad band, like lots of bits per second data, but it's not very high amplitude, you'll get these sort of blue streaks, where each one of those blue streaks is actually a digital data stream. Now, the one that's really weird is the one just to the left of this orangey column, and you see these little orange spots every so often. That's actually a one-way pager, because it only sends data, real data, when there's a page, and there's not always a page. So it'll, because the paging channels are shared, it'll send out a page, and the page data transmission might not even last a full second. So it gets very compressed, but you can see the signal, and then it's gone, and then more signal, and it's gone. Now, these orangey things here on the right, those are voice. Those are music. Those are like radio station kinds of stuff. And voice is very dynamic in frequency, and it can be soft, it can be loud, and you're doing that all the time in real time. So voice is always very easy to pick out in a waterfall. Data is always very easy to pick out in a waterfall. This blue one here that's got, very nice, distinct, solid edge bars, that is very high-speed data. So by having the waterfall, you can readily pick out, oh, there's voice, there's data, there's a pager, there's just some low-speed data, oh, there's high-speed data. So you can actually, once you have it in a waterfall format, you can actually very readily tell what you're looking at. So once we have the waterfall format, the
Yeah,
underlying.
Monroe, let me just mention what I didn't realize about this is that it's not only like the output of a graphic equalizer,
Yeah,
it
it
is the
is.
output of a graphic equalizer, that
Yeah.
all of these things are just, when you say, okay, I want the bass turned up high and I
Mhm.
want the mid-level turned this way, that this is just spread out the frequencies into certain groups the same
Yep.
way, and then it's spreading it out over time.
Yep.
It's neat.
So you start with a simple waveform, which is an amplitude of a voltage measured over a time domain. And then you start processing it. But the amplitude and the time domain can be anything. It doesn't necessarily need to be a radio signal. It could be audio. It could be noise. It could be a pressure wave from, a change in weather. It could be elephants walking on the ground at, producing low frequency. It can be any sort of signal that is changing in voltage value over a time period. And then you can do all this math to the back end of it. So once we have our waterfall, we can change the rate that the waterfall scrolls up and down. We can change that data bit from 8 bits to 16 bits and get a lot finer resolution on it. We can go in there and play with the scrollers to say, I want the waveform changes to be brighter or darker. I want the amplitudes to be brighter or darker. So you can play with how, if you don't want the high-speed data to be as obvious, you can crank more towards, I just want to see the dynamic stuff like voice. So all of these things can be adjusted. If I want to just uplift the signal, I can go back to my original waveform and just add to the display. I don't change the actual signal. I just change the value that's displayed, and the whole waveform now moves up or moves down. I can expand it vertically. I can expand or compress it, even without changing the frequency of the data. So I can do all this stuff with signals once I have them in a mathematical format. So when it comes to physics and chemistry and astronomy, and even some electromagnetic spectrum, once I have my waveform going over a series of frequencies and I have my amplitudes, I can look for, okay, my signal, and then, hey, there's a black line there. That's an absorption line. I can go in and find out what the actual frequency of that absorption line is, flip it around from cycles per second to wavelength and say, oh, the presence of that dark line means I have this particular kind of carbon in the light coming from my signal. Or if it happens to be in audio, I can detect, oh, the room that I'm in is creating a nodal zone and subtracting out a certain frequency of the audio. So all of these relationships work not just for what you're familiar with them, they work across a very broad set of observational analysis.
Monroe, you said nodal room?
Yes.
Nodal?
Let me explain it this way. If you're in a room, there's a lot of loud music going on in the room. If you walk around the room, you will find spots in the room where the waveform of the audio wave cancels itself because it's bouncing off of a corner wall. So the waveform hits the wall one way, goes off the wall the other way, comes back, and that waveform actually overlaps and cancels itself out. So in a loud room, you can actually find what is known as a nodal zone. This is where the acoustic sinusoidal wave cancels itself, and the room's quiet or standing right there. But
Is
if
that
you
what they
move
call
away from there, the room gets louder.
what's a standing wave? Is that a standing wave?
A standing wave is usually you're taking two waves and you're overlapping them.
Yeah,
And when you have the two waves precisely overlapped peak to peak and valley to valley, you have a standing wave. They're in harmony with one another.
right. They
You
could be
can't.
bouncing off a wall,
Yep.
two different walls.
Yes. And you can actually change the harmonics of it and make the peak match the valley and the valley match the peak. And now you're essentially nulling, you're subtracting out the peaks and the valleys, and it's quieter there.
Yeah.
So whenever you're in a room that there's a loud noise and you see me walking around and then all of a sudden I stop, it's quieter there. So it all gets down to this thing that guy Einstein came up with in the early 1900s, this photoelectric effect, where if you have a photon hit a particular kind of material, it releases electrons. And if you have enough photons releasing enough electrons, you get a voltage, and then you run that analog voltage through an analog to digital converter, which is a ladder of resistors typically for successive approximation, and you'll get a number. And if you do that very rapidly over a period of time, you can capture a frequency, a waveform. Once you have that defined, now you can do your math with it. But if you want to boost the signal, if you happen to be the Large Hadron Collider over in Europe, your voltage level is going to be in billionths of a volt, which is not easily measurable. So what you do is you run it through a lot of low noise amplifiers to get the signal up where it's high enough that it matches the range of your analog to digital converter. So you may start out as a billionth of a volt, and then eventually you wind up being millivolts after going through a cascade of amplifiers. And those work in radio too. Those are called low noise amplifiers. And you can change your sampling rate. If you have a waveform that has a very high frequency and you're not sampling it often enough, you may not see the actual shape of the waveform. Nyquist-Shannon says, if you want to capture accurately a waveform in cycles per second, you need to actually sample it at 2 times n to catch all the different points along the shape. So you need to make sure your sample rate is fast enough, that your amplitude is good, that you have low noise, that you have a good analog to digital converter that's reliable and doesn't produce synonyms like it's close, it's right on the edge, so it'll give you this value or the value below it, and it's just wiggling back and forth, so you'll have jitter. So you deal with all that kind of stuff, and then how are you capturing the data? Is it truly plus and minus like a waveform? Because if you get into the I and Q sampling of amplitude and quadrature, it's positive only. So they just scale it up so it fits nicely into a 0 to 255 range. And then are you transferring the data that you're capturing parallel through a bunch of wires? Are you capturing it serial over a single wire? How much of the data how much of your data rate, your available bandwidth, is being consumed by taking the raw data and making it into computer usable data, the framing of it, the administrative overhead of it. And all these things go together to get, here's my raw data sample rate with high accuracy. Now, once you've got that, if you want to send that from one place to another, now you got to talk about putting additional framing and encryption for your signal and whatever your wired or wireless service provider is to get that data somewhere. Sometimes I'll run my software-defined radio receiver on a little Raspberry Pi to get the highest sample rate with the greatest accuracy. And all I'll do is I'll feed the raw sampling over a wired Ethernet connection to like my Windows machine, because the Windows machine is much better at displaying things graphically. So I'll actually separate the two parts of my radio receiver and have the front end processing and then the back end presentation processing. So in conclusion, I knew this was going to be a short session tonight. Waveforms are simply measurements from a sensor over a band spread of frequencies. So I'm measuring a voltage and how often I'm measuring it, and that gives me my data. Once I have the data, I can present it in several different ways, just as columnar raw data, or I can go in and do analysis over time. I can do spectral analysis, or I can do my fast Fourier transform and then display it as a waterfall plot. So I can now look at it and just visually go, there's data, there's high-speed data, there's a pager signal, there's voice, there's an FM radio station. And once I start showing you the FM radio station, you can actually see which radio stations are digital FM and which ones are analog FM just by looking at the waterfall. And to understand how much data you can process per second, there's a whole lot of factors that are involved that only people like myself need to get deep into that weeds. And as usual, lots of links, more links. And then because a lot of things like that angle as it rotates are not measured in degrees, they're measured in radians. You may not have remembered radians from high school, but there's a link to radians. Now the Fourier transforms. When I started looking at the Fourier series and then the transform was pretty straightforward. I only got one video for that. That's just the discrete table that does the transform. But if you want to see how a Fourier series changes over time, I've got, if you want the formulas, there's a video for the math-minded folks. Then for the folks that just want to see the waveforms moving up and down or on a circular dial, the visual method. And then the folks that actually want to see like a 3D computer simulation of it, so you can actually see the quadrature waveform and how it stretches out in 3 dimensions. That one's really cool because it's, it looks like little tinker toys in 3D animation, and it moves slowly, so you can actually see if I take this algorithm and then I add on this algorithm and then I add on this algorithm, you can actually see in the series how it starts to smooth out the waveform to whatever you want it to be. And then for the people that want to go write some software, yes, there's a link for how you would do your fast Fourier transform using Python libraries. And then just an example of how a digital signal processor works to demodulate a particular kind of signal. And then once you have your digital signal, how do I do things like, I want to remove background noise. Well, if the background noise amplitude is below a certain level, then you can just subtract that off and get a clean signal just by clipping the bottom off. Or if you have a lot of high frequency spikes, you can actually go in and do a frequency transform and subtract out the high frequency spikes. Or if you've got something like, I have a piece of music and I want to subtract the vocals out of the music. Well, once you have the acoustic wave of the audio, you can take the vocal range, which is different than the instrument range, and you can subtract out all the frequencies that would be human vocal range, and you can subtract the vocal out from the audio, from the instrument track.
Come get snuggled.
Yeah, but aren't you also ruining some of the music then, if you're taking out some of this?
No, because it's frequency crossing. Remember, you're not taking out the peaks and the valleys of the instrument data. You're only taking out the frequency range of the peaks and valleys of the vocal track.
But aren't they, don't they mix? Aren't there plenty of music frequencies?
The signals actually cross.
Oh.
So if they cross and you take out the peaks and valleys of the vocal, you're not going to be attenuating the instrument noticeably.
I know that exists. There's plenty of these remove the vocal from.
Yes. And that's all they're doing. They're just taking the acoustic signal, converting it into a Fourier transform, and then doing waveform analysis on it and subtracting the vocal range out.
And you don't lose any of the music.
Have you ever looked at these services that do remove vocal tracks and go, where'd the voice go? Yeah, they're pretty good these days.
Yeah, they are. Yeah.
But it's also a matter of what's the sampling rate, how many bits per sample, how long is their Fourier series? Yeah.
But isn't this like that? This is Joanne. I'm asking a question. Is that okay?
Yes.
Okay, I thought maybe somebody else was asking a question too. Okay. Isn't this like the crime movies that they're always showing how they filter out some kind of wave, and they're showing all these waves on the thing, and then they say, now we have the bells in the background.
Well, you have to have a basis for it. So if, for example, you had the recording of a crime scene and in the background you heard a clock tower bell. But there's a lot of like automobile traffic and people talking.
Right.
You know what frequency the bell's ringing at because you can actually see the peaks and valleys on the waveform. So you know what you want to keep. And if you invert that, you now know what you need to remove. And it's pretty straightforward once you have it as an algorithm to subtract out everything but the bell sound. Now, once you have the bell sound, you have the peaks and valleys of the bell. And if you have a catalog of bell tower sounds in your city, you can know which bell tower that was. And the second thing you can do is, if you know the amplitude of the bell that you're hearing, you can actually time the distance and determine how far away the microphone was from the bell. So we know where the culprit was at that time of day because it was striking 3.
Or underwater, you can tell whales from submarines.
Oh, absolutely, yes. In submarines, the sound systems, most people think of it as sonar. That's if it sends out a signal, it reflects off of something, you get the response back. But there's also hydrophone signals where you don't send anything out because that would give you away. You just listen. And when you listen, you do the spectral analysis. And if you remember the movie Hunt for Red October,
Right, the
it showed you
cavitation.
that vertical scrolling waterfall, and you could see where the biologic was versus the man-made thump engine. So yeah, in the movies, Waterfall, who knew?
Yeah. And Captain,
Yeah,
there'd be whales
and
here.
now the algorithm is so automatized that if you make like, let's say, a video on YouTube and you have a background music that needs copyright play, like when you play the video on Facebook, it is already automatically remove the background music that you don't have rights for it because it was in the background in a public space. And it only comes out your voice. It's amazing because it's like it takes seconds and the thing is just removed automatically.
Yeah, they used to just mute out the sound.
Yes, Facebook does that. YouTube still deletes your audio. So I have to be careful what I play in the background. It will detect audio during your upload processing, and it does analysis for copyrighted works. And I think you're given about 3 seconds worth of leeway that you can accidentally play some copyrighted work for about 3 seconds, and it'll go, okay, you fall within the guidelines. But beyond that, if you're playing a copyrighted work and it's in their catalog of copyrighted works, because the producer said you must look for this or else, they'll remove your audio track completely.
Right. Yeah.
The video is
You know
still
what?
there, but it's like
You know what the Miami Beach police used to do?
No.
They wouldn't mind people videoing them when they were arresting people and stuff. They would just turn on Disney music at the same time.
Yeah, that would mean your
So
video
that you
video
couldn't
gets
post
outlawed.
it anywhere.
Yeah. Well, YouTube will still allow you to post. They just mute your audio. I remember back when Helen and I were at the City of Fort Lauderdale New Year's Eve event, and we were just doing a video. She was recording a video of her and I at the event with the band on the stage in the background. We didn't know what they were playing. We didn't even recognize the band, but her video got basically removed. This was years ago before Facebook would remove the music because it contained a copyrighted work. And we had to go back and go, can we at least keep the video? You can mute the audio. So, yeah.
You know the shot detectors that the police use now in big cities?
The shot.
Gunshot detectors.
Oh, yeah, right.
They have phones and microphones, and they can parse the signal and tell if it's a backfire or a firecracker or if it's a gun, and then where the gunshot is, and before anyone calls in, get police on the way over there.
Yeah, all you need are microphones. You need at least 3 microphones sort of in a triangular pattern. And they don't need to be anywhere near the gunshot because if they're up high enough, the sound's going to propagate. So they'll put microphones on cell towers. And, you know, if you have a shot in a neighborhood that's off in that direction, the sound wave will reach one tower before it reaches another tower before it reaches another tower, and they can triangulate it in a fraction of a second.
And I think they've been using that for more than 20 years. It's
Yes.
not new stuff.
No, but that's just once you have your sensor data and you convert it into numbers, and the numbers are in the right form, like a Fourier series, there's all kinds of processing you can do. Okay. Comments? Questions?
This stuff is practical.
Oh, very much so. And it's in your phone and you don't even pay attention to it. It's just there because it's so valuable to just have the capability there that people don't think about it. The part that really expands people's thoughts are they might see it in one thing like audio signals or radio signals. And it doesn't click that same waveform analysis works on anything where you have a voltage measured over time. Now, it could be ultrasonic waves from undersea creatures, or it could be, light out in space. Doesn't really matter. The signal algorithms are not that much different. I remember when I was doing astrophotography and doing radio astronomy at the same time and was looking at the post-processing. So in imaging, you take images periodically, and then you add them all up and you divide by the number of images you have in your stack. It's called stacking. In radio astronomy, you're dealing with just like one two-dimensional signal, and they used to do that on chart paper. Like it had a little ink needle, and the ink needle moved up and down with the waveform of the radio signal, and the chart paper wasn't in a roll, it was in a Z-fold fan fold. So how would you describe that? Well, like the Z-fold. So the same image processing in radio astronomy is stacking, folding, but they're both doing the same thing. They're taking the values of the samples and adding them up over time and dividing by the number of samples to get rid of random background noise. So a lot of the things that you use in one area works pretty much the same way in another area. You might have different limits, might have different frequencies. Your sensors might have to be amplified more, but all this stuff works the same way at the Large Hadron Collider as it does in your mobile phone. It's just bigger scale.
Recently, you corrected your mic to have a better quality sound in your voice. And was that a waveform that you were correcting, or?
I bought a small cheap box that was under $20. It's a 2-input microphone and line-in preamplifier. And it's a digital preamplifier. So it's actually digitizing my voice and then improving the waveform, amplifying it, and then sending it out as an analog signal. So it actually has a digital to analog, it has an analog to digital on the front, and then a digital to analog on the back, because it produces an analog audio out into my microphone jack on the computer. So I'm just not a big fan of all these social influencers with the microphone, the big black thing in front of their face, or it's on a boom arm that covers half their head. I just don't see that that's necessary in order to be able to reliably pick up your voice. And I throw a lot of the acoustic dampeners on. I've got 1, 2, 3, 4, 5, 6. I've got 6 on the walls right now, and I'm probably going to be putting 2 more in because I can hear just a little tiny bit of echo off that wall over there. So I'm going to throw 2 more. They're hexagons. They're sort of very stiff, dense foam hexagons that are about 1/4 of an inch thick. They're just like hexagonal things, and you just slap them on the wall wherever you want to deaden the sound, and they're pretty good at deadening the sound.
There are instruments that can spin around in a room and find where echoes are.
Yes. They found that your home stereo system, you can actually add a microphone to the actual home stereo receiver, and it can send out infrasonic sound that you can't hear, and it'll do an acoustic profile of your room
Oh yeah.
to give you better surround sound.
Oh yeah.
So
Well,
yeah,
it works in ballrooms too, and
yes,
theaters, classrooms.
yep. Once you have it as numbers, you can play with the numbers, and how you play with the numbers doesn't change much when you go from, one kind of equipment to another. Oh no, they
Oh,
could
by the way, I like the little like, subscribe, notify, share.
Yeah, I added those about 3 weeks ago. The very first slide has that, and the very last slide has that, in case people go, I wasn't so bad after all. Maybe I'll indicate like of that. Or I want to see some more of this crap from this guy. I'll subscribe and let me know when he posts stuff.
Yeah.
Interesting. Good to learn.
Okay. So anything else before we close for tonight?
No. So, Merry Christmas to everybody.
Merry Christmas,
Yes, Merry Christmas,
everyone.
everyone. And
Happy holidays.
Feliz
Merry Christmas.
Natalis.
we'll talk again next week before the new year.
Right.
All right.
Sleep well.
Thank you.
Thank you. And sleep you well, everyone.